Hello Science Alliance, hello IGCSEers, I'm Lara, this is Theatre of Science. I stream free live lessons to home educators. This one's very exciting for me because I am actually trained to teach science, physics to A-level, and IGCSE, to be perfectly honest with you, for me sits somewhere between the regular GCSE and A-level. So we're getting to the fun bit. Yeah, I love that you're here. Right, it's quite a nice little standalone lesson, this. It's actually lesson 2 of the energy module. Usually I say you can jump into the start of a module, it's a good time to start. We did about energy stores last week, about how elastic bands sort of are a store of elastic energy, or your body is a chemical energy store. And I said this week we would do pathways, but actually one of the pathways is heat. So I thought we probably better talk about what heat actually is first of all. So let's do that. Just a quick quiz. Some of you will know this already, but if you don't know, you have to know it for today. So let's go through it. You've got 4 little diagrams here, boxes with, well, just balls in. We'll talk about atoms in another module, but for now, these are all particles, okay? Can you please tell me which one of these images best represents how the particles are arranged in a solid and a liquid and a gas? We won't spend long on it because if you know, you know, and if you don't know, you would probably want me to just tell you. So you could label them if you like, if you've got the free optional worksheet from my website, or you can just think about it. One of them isn't a good model for any of them. So one of these shows what the particles of a gas look like, the air around you. One of them is a reasonable model for what like the particles in my coffee are like, and one of them is a good model for what a solid is like. And the 4th one is the one that people always draw in their GCSEs, and it's wrong. I'm going to give you, like, I don't know, the time it takes me to sip this coffee. Which one's a solid, which one's a liquid, which one's a gas, and which one is not anything really. I'm liking having comments on YouTube. I'm seeing the comments on YouTube, but I'm trying not to talk about it too much because some people find the comments distracting. And hello, Casper. All right, Margaret, I said I wouldn't mention them. Well, I won't. Okay, here we go. So the solid is the one where the particles are really densely packed together. The particles in solids are very, very firmly bonded together. That's probably not a surprise because most solids is quite difficult to squish them, isn't it? Because look, their particles are all crammed in together, all touching, bonded together. Gas, the particles are really far apart. They're not really experiencing each other at all. They've got loads of energy, they're just flying around. The liquid's the one that gets people always confused. Particles in a liquid, they are actually touching each other. It's kind of like a ball pool. They're sort of moving around each other. The bonds are constantly forming and breaking. This one at the end is what people always draw when they want to draw a liquid. But this is just a sort of gas where the particles are weirdly close together. And just finally checking that you know, a place with no particles at all is called a vacuum. If it was just a yellow box with no dots in, that would be a vacuum. So space is a vacuum, okay? Right. Good. It's time for our activity. I didn't make this activity up. If you watch Veritasium, fantastic science channel on YouTube, Veritasium did this. There's a video where he just goes around asking people the answer and making them all confused. It's brilliant. Have you got a metal spoon and a wooden spoon? Space contains some particles, I've been told in the comments. It's pretty much a vacuum. Get a metal spoon and a wooden spoon. Just keep them on the table for now, please. It could be anything wood and anything metal, to be honest. I'm trusting that they've both been in the same room for quite a while. So I haven't kept like my wooden spoon in the fridge. My metal spoon hasn't been in the oven. So if the temperature of this room is 25 degrees, the spoons are going to be 25 degrees as well, right? Because they're not mammals. They're not like generating their own heat like I am, so they're going to be the same temperature as the room, yeah? Like this salt is, like this whiteboard is, right? Well, pick up your wooden spoon and your metal spoon. Really get a good grip on the spooniest bits of the spoon. What do you notice? Let me close your eyes. Give them a feel. Notice anything? Notice anything about their temperature? Would you say that one is warmer than the other? Cooler than the other? What do you think? Switch hands if you like. It's a good puzzle, right? Are you saying that the metal spoon is colder? What is that? The metal spoon, is the metal spoon colder? How can the metal spoon be colder? They're both big thank you. So Karen in the comments, yeah, people in the comments saying the metal spoon is colder. This is how everyone feels. But they were both in the room. They're both in the same room. How can it be that one is colder? What a great puzzle. The answer really basically is that metal is very good at stealing heat from your body. And the wooden spoon is not very good at stealing heat from your body. So they are in fact both the same temperature, but your body is warmer, right? You're a mammal, you eat food and that body, I'm trying to say energy words in a correct way because it's IGCSE physics. You fill your chemical energy store with energy we learned about last week. Your particles in your body are moving around a lot. Generally speaking, if things have more energy, the particles vibrate more. So the particles in your hand, they're moving around a lot, they've got a lot of energy. That's kind of what it means when we say that something is warm, right? The particles in the wooden spoon are not moving around as much. So what is happening is your particles in your hand are knocking into the particles of the wooden spoon and making them vibrate more. And this is basically what conduction is. It happens in solids. It's this kind of domino effect. And if you held the spoon for a really long time, then eventually you would probably find that the handle of the spoon eventually became warm. How warm is it going to get is the other thing. How warm eventually is this spoon going to get? Is it going to get to your body temperature? Is it going to get to like 100 degrees? Is it going to get to 600 degrees? Is the spoon going to melt? How hot is this spoon going to get before our conduction stops? Drop some particles on the board while you're answering that. So these are the, shall I do colours? I got all these blooming coloured pens and I never use them. I'm not going to use them in IGCSE physics. When am I going to use them? These are the particles in your hand. We'll make them red because your hand is warm. And then these are the particles in the spoon. And what's happening is they are sort of coming into contact with each other. These particles are vibrating more, you see, because red. And those vibrations are making this particle vibrate, which is making that particle vibrate, which is making that particle vibrate, and so on until all the particles are vibrating. Exactly, yes, well done. In the YouTube comments, people are telling me it will get to your body temperature. It can't get any hotter than that because we talked about last week how you can't just make energy. How could it possibly get hotter? That these will only vibrate as much as these are vibrating. But yeah, so this is what conduction is. Like I say, happens in solids because they pass heat on through vibrations. I'm going to keep saying dominoes. Don't say dominoes in your exam. The energy is transferred by particles vibrating into each other. All right, I think I've told you enough to have a go at these questions. I've just got 6 examples here of heat being transferred. And I want you to tell me, is conduction occurring, yes or no? Here we go. Is conduction occurring? I gave you the option of saying a bit. So yes, a bit, or no. We've got the sun heating the surface of a swimming pool. So here is the sun in the sky. Here is the water in the swimming pool. The sun's heating up the swimming pool. Is that conduction? Yes or no? Soup heating on a stove. We've got a metal pan here with some soup in it and it's on the stove. Is that conduction occurring? Yes, no, a bit. A radiator heating a room. Yes, no, a bit. If you don't know how radiators work, they've got very hot water inside them. So it's metal tubes with hot water in them and then air around them. Heat escaping through the glass of a closed window. So it's nighttime outside, it's cold, it's warm in your house, you've got the windows closed. Heat escaping through the glass of a closed window. Is that conduction or not? The handle of a toasting fork getting hot. Is that conduction, yes, no, or a bit? And over here we've got a fire and a marshmallow not touching the fire and the marshmallow going brown. Is that conduction happening? And I've said question number 2, if it is conduction, can you explain what the heat is conducting through? Draw a diagram if you want, or say it with words. What is the heat actually conducting through in each situation? I will draw a picture on the board of each one. It's part of anything else that will slow me down a bit. Also, it's fun. Yes, I just remembered that I have coloured pens. A lot of people were getting one wrong on Facebook yesterday. So much so that I started thinking that maybe I was wrong, but I don't think I am wrong. I'm also drawing diagrams to show like what direction the heat is being transferred as well. Okay, I think that'll do. Yeah, I think that'll do. Right. How have you got on? All the conduction. Is that Casper saying that? No, they're not all conduction. That is the kind of mean trick that I would play. But no, they're not all conduction. I'll give you a few more seconds. If you're bored, you can always like and subscribe, can't you? And I don't know, sign up to give me real cash money if you like, but obviously ask adults in your house first. Oh, and there's always a post on Facebook. If you're not commenting, but you have a Facebook account, there's always a post on Facebook when I'm live on YouTube. So you can go over there now if you want to and comment on that. Or you could just lurk and know that I appreciate you being here anyway. Right, let's go through it, okay? The sun heating the surface of a swimming pool. Do you know what? I'm just going to tell you first of all. We actually, on this course, we learn about 3 different types of heat transfer. This is the first one, conduction. Next week, we're learning about convection. And the week after that, we're learning about radiation. Now, obviously, questions like, is this conduction, are a lot easier if you know about convection and radiation, because you can go, oh, no, that's not conduction, because that's radiation. So this is a bit mean. So if you haven't got it, don't worry. By the 3rd week of these, you will have got it. But no, the sun heating up the surface of a swimming pool, that is not conduction. That is not like a kind of domino effect. It's something else. Conduction happens in solids. Soup heating on a stove. I've said that, yeah, that is conduction. I drew this cool little diagram here. So we've got the fire down here, and we've got a metal, which is a solid, and then we've got some soup here. So this row of metal particles right next to the fire, that gets hot, that starts to vibrate more, and those vibrations are passed along. The next particles start to vibrate more, and then eventually that heat will travel all the way to the soup. A radiator, yeah, I've put a bit. We're going to do a lot more about this next week, but the radiator is made of metal, and heat, if this is like the radiator tube here in the middle, and that's the really hot water, then the hot water heats that particles in contact with it, and they vibrate more and bump into the next particles and bump into the next particles, and eventually that will heat some of the air in the room, but more of that next week. Heat escaping through the glass of a closed window. Everyone on Facebook was saying that no, that wasn't conduction. That might be because you know that glass isn't a very good conductor. But if that were to happen, then yeah, that would be conduction. I tried to draw you a picture. So this is the inside with the warm air particles. This is the outside that's all chilly. So the warm air particles would bash into the glass, the solid glass, and make those particles next to the warm room vibrate. And eventually those particles would vibrate into each other until the heat was transferred to the outside. But it would happen very, very slowly. The handle of a toasting fork getting hot. Yeah, I didn't bother to draw that one because that's just the same as the spoon, right? And heating a marshmallow near a fire. No, that's not conduction either, because there's this gap here. So it's not a domino effect. Particles of air aren't bumping into each other to get to the marshmallow. But that will make a lot more sense in a couple of weeks' time. Really sorry. Right, which one of these is the odd one out? Of all the ones that, yes, they are conduction, which one of those is the odd one out? Heat escaping through the glass of a closed window, soup heating on a stove, a radiator heating a room, or the handle of a toasting fork getting hot. I've sort of already told you, haven't I? Which one's the odd one out there? It's, well, you could probably, you're all very creative, you can think of loads of different reasons. It's the glass, right? All these other things are made of metal, and metals are particularly good conductors. They're very good at transferring heat energy. And it's because they've got these things called free electrons. This is called like a lattice. This is the structure of a metal. I think it's called a lattice because, I don't know, people used to eat a lot of pies in the olden days when they were naming physics stuff. So yeah, these are I don't want you thinking that these are protons. We will talk about atoms later, but basically these are atoms of metal, but they've lost a little bit of negativity. The atoms have got electrons going around them. So this is still an atom, but some of the electrons have popped off and are just free to move around. So if you came to electricity lessons, that makes a lot more sense to you. Because we talked about how electricity is just charged particles flowing, and metals are really good at allowing electricity to flow through them, because as well as having these particles, like all solids do, sort of fixed in place, vibrating on the spot like that, they've also got these little free negatively charged particles which can zip around, and that makes them good at conducting electricity, but it also makes them very good at conducting heat. So if you get a question about like why is metal a good conductor, a good thermal conductor, you can say because heat is transferred through it via vibrations, and also because metals contain these free electrons which they're just free to move around. All these particles are sort of fixed, vibrating on the spot, but these ones can zip around a lot faster. Right, something that conducts heat very poorly is called a good insulator. Let's do the activity. So if you're doing this next activity with me, you need some butter or some margarine. It can be any kind. And you need to make a little butter cup on your hand. Butter cup. So put a little cup of butter or margarine. It's quite melted actually, it's quite hard to do. You just need a little blob of margarine that you can put an ice cube on. If you come to my Lego show, maybe you think you're too grown up for the Lego show because you're watching my IGCSE physics lesson. You're wrong, they're awesome. Last week we learned about otters, sea otters and river otters. And we actually did this activity then. But we need to go into more detail because this is IGCSE physics, right? But yeah, and if you've done this already, just do it again because it's brilliant. So you need a butter cup on one hand, and you just need a hand on the other hand. And then the idea is you get 2 ice cubes. If you've only got one, that's fine. You can pass it between them. But put an ice cube on the butter and an ice cube on your skin, and then wait and see what happens. And don't be a hero. Just don't be a hero, okay? Don't hurt yourself. Ow! You will find very quickly the bare hand that is holding the ice cube becomes very painful. It's absolute. Ow! Ow! It feels like it would be bad telly to just drop it straight away, but it really, really hurts. So hopefully you can tell me now. You can tell me why that hurts. You can tell me what was happening, right? And it's more dramatic than with the metal spoon. It's basically just a more dramatic version of this, isn't it? Holding an ice cube. Why is it more dramatic? Why does it hurt more? It's because, give thinking time. It's because there's a much greater temperature difference. Colder, yeah, exactly, Wendy in the comments. Yeah, there's a much greater temperature difference between your hand and the ice cube. So heat is being transferred much faster from your hand to the ice cube, which is very painful. The little buttercup, if you've got a good buttercup going, I could do this all day. It's so easy to do. So yeah, I should say, eventually that ice cube will heat up until it's your body temperature, right? So it's a lot of heat energy that's going to have to go into that ice cube. Yeah, this is so easy. So in last week's otter lesson, we looked at how a lot of marine mammals, they're warm-blooded, they need to keep warm, but they spend their whole lives in the sea. Like, what is with that? A lot of them have got a layer of blubber, this thick, sort of fatty-like stuff. Blubber is a very, very, very poor conductor. It doesn't allow heat to travel through it, so it's protecting your hand in this case. Stuff that is not a very good conductor is called an insulator. So that blubber is a really good insulator. It doesn't let heat travel through it. We also learned, well, actually, I'll tell you this first. I mean, I think you probably already know this. Oh, This is a good comment which will help everyone. The coldness is being trapped by the butter because butter is not a good conductor. Okay, brilliant. Right. Oh, I'm so glad you said that. And I don't want to I don't want you to feel like I'm criticising you. This is why comments are really helpful, because they help everyone. Be really careful with the word coldness. We'll do a lot more about heat. In fact, we've got loads of lessons on heat, so we don't need to know this now. But all coldness is like lack of heat. So coldness in science, I suppose, is not really a thing. You want to talk about the heat, not about the coldness, if you know what I mean. So the insulator, you're right, the butter isn't a good conductor. So it's stopping the heat from being transferred to the ice cube. It's not stopping the coldness from going into your hand. That's a very good point. Actually, we'll talk about this later, but heat always travels from hot things to cold things, never the other way around. Because you're right, actually, someone who isn't a physicist might well say the coldness is going into your hand and that's why it hurts. But that is not what's happening. Right. Are liquids and gases good conductors? That's that one, didn't I? Picture of tortoise. Are liquids and gases good conductors? Do. Oh, God, what an annoying little sound effect. The countdown theme tune for any gases questions. But I feel like if you don't know this, then I just need to tell you straight away. No, they are not. You can hopefully see by looking at these little particle models, liquids and gases are generally speaking really not very good conductors, because heat can't be transferred by vibrations. I mean, look at those particles of gas. They're miles apart. It would take absolutely ages for that particle of gas to whack into that particle of gas and for the vibrations to be passed along. And to a lesser extent, it's the same with liquids. So solids are very good conductors. And generally speaking, liquids and gases are good insulators. They're not good conductors, they're good insulators, which is kind of the opposite. They don't allow heat to pass through them. So in the otters lesson last week, we found out sea otters are one of the only marine mammals that live in the sea, that don't have this thick layer of blubber. What they have instead is ridiculously dense fur, and they fluff it up and fluff it up and fluff it up so it traps air, because air, as hopefully you've seen from the little particle diagram there, air is a very good insulator. It doesn't allow heat to travel through it. So if you can't be blubbery, be fluffy is the lesson that nature tells us. And you might have seen on the screen what I'm going to just quickly say now. You've heard of a vacuum flask? Flask keeps things cold or hot, the drinks inside them. Maybe called a thermos flask now, but traditionally called a vacuum flask. This is why, look, because they've got a vacuum in them, right? They've got this layer that doesn't have any particles. So how is heat going to travel from, say, this hot drink out to the cold atmosphere, or from the hot atmosphere through to the cold drink? It can't possibly, can it? Well, it can, but we'll learn about how in a few weeks' time. Right? I've got this layer. Oh, echo, yeah, God, that's so annoying. I was wondering what that was. I'm just going to turn the volume off on my phone. Is that better? Wow, how long has that been happening for? That was interminable. Okay, well, we've nearly finished the lesson anyway, luckily for us. Have you heard of Baked Alaska? If you want some homework this week, have a go at making Baked Alaska. It's got ice cream in the middle and hot meringue on the outside. You can tell me how that works now, right? How does that work? What's meringue doing? I didn't let them think about this on Facebook, but I'm going to give you 5 seconds. How is Baked Alaska a thing? You get ice cream, you surround it with meringue, you stick it in the oven, the ice cream stays cold, but the meringue bakes. What's that about? Are you telling me that meringue has a lot of air trapped in it? Yeah, the air mixture, you beat egg whites to make meringue. So there's loads and loads of air trapped in this meringue. So the heat from the oven cannot conduct through the meringue to get to the ice cream. Insulator, brilliant, well done. Yeah, insulator, fabulous. Whew, right, you lot. I think that is actually pretty much the end of the lesson. Quick shout out to double glazing. And of course we've got to go through the I've got a little puzzle for you, a little practical puzzle. So yeah, glass is actually a very good insulator. It is a very poor conductor. It's a good insulator, doesn't allow heat to pass through it easily, but just to be on the safe side, double glazing is a sheet of glass and then air in the middle and then another sheet of glass. So you've got loads of insulation there. And that's why in your loft you might find lots of fluffy stuff like this as well, because it contains a lot of air. So basically just working the same way as the sea otter, it's not allowing heat to pass through it. Right, if you've had a look at your IGCSE physics specification. If you've been to my website, you've got the free printouts. There's a little list on the side of all the things that you need to know. There's an experiment. It's not an activity, it's an actual experiment that you can do to work out which material is the best conductor. And I thought, I could show you a picture of it, but you probably won't remember, right? I want you to imagine you've got all this stuff in front of you and see if you can work it out. It was melting people's brains a little bit yesterday, but I feel like it's good for you. So imagine you've got a Bunsen burner on the desk in front of you, so it's connected to a gas tap. It's like you've got this nice steady flame burning, okay? You've got some drawing pins here, these boring metal drawing pins. Tub of Vaseline, which is basically glue that melts when it gets warm, bit of glue. You've got a tripod, a stand to put stuff on. And you've got some rods made of the materials that you want to test. Could be anything you like. Let's say you've got a glass rod, an aluminium rod, and a copper rod. And you want to see which one of those allows heat to pass through it most easily. Which one of those is the best conductor, all right? I'm going to give you a few seconds to just think about it. Imagine those on your desk. What are you going to do? What are you going to stick to what? Where are you going to put it? And this is kind of an extra question, but it's also a bit of a clue. Why couldn't you use these drawing pins? So you've got a drawing pin here which has a big colourful green plastic handle. Why couldn't you use those drawing pins? You might find this brain melting really difficult. That's absolutely fine. It's kind of the point in a way. I just thought if I tell you, then you won't remember it as well, as if you've had this little bit of pain beforehand. This silence, by the way, is me trying to draw a tripod on the board. You can't use the drawing pins since there is nothing to stick them into that will not break the tip of them. No, you need to be thinking about, what we've just talked about, what allows heat to travel through it and what doesn't allow heat to travel through it. These ones have got a metal end and these ones have got a plastic end. What on earth is this experiment where you can't use drawing pins with plastic ends, eh? What a horrible, mean, evil question. I love it when I do this. Like, hey children, here's a question. Pretending that I would have had any idea if I hadn't just been taught it. But anyway, shall I flip you around and show you? You've got the time it takes me to draw a little Bunsen burner flame. There we go. Wow, that is very weak. Okay, right, doesn't matter at all if you didn't get it. I'm going to tell you about it right now. So what you do is, I love this, very clever. I don't know who thought of this. What you have to do is, exactly, plastic is a good insulator. So you get your tripod, as demonstrated beautifully here. This is the tripod. This is the Bunsen burner. You balance all the rods on the tripod, so they're all in the Bunsen burner flame. And then you get your Vaseline, your glue that melts when it gets hot. And you put a blob of it onto the end of your drawing pin, and then you stick the drawing pin into the Vaseline like that. There we go. And then you just wait and see which one falls off first. How good is that? So the one that's the best conductor, the vibrations will, the particles in the metal or wherever it is, will transfer energy really quickly, and the end will get really hot and the glue will melt, the Vaseline will melt, and it'll fall off first. Whereas like the glass rod, is a good insulator. So the heat will travel, it will eventually travel, but it will travel extremely slowly. So that drawing pin will fall off. And then you put a balloon under them. Wendy's saying in the comments. Yeah, exactly. That's good, isn't it? I thought of something else I was going to... Oh, yeah. So the reason you couldn't use plastic drawing pins is... Well, actually... Oh... Do you know, I didn't notice this on Facebook yesterday, but I've just noticed it now. It wouldn't actually make a difference, would it? It wouldn't make a difference. Because why wouldn't it make a difference? I've made a mistake now. Using plastic drawing pins wouldn't... It's not a problem, is it? Because what is happening? You're heating up the Vaseline, and yeah, exactly. The Vaseline is the thing that needs to conduct heat. The Vaseline needs to basically make the thing let go and it becomes a liquid. But yeah, actually, you don't need heat to be conducted through the drawing pin, do you? Yeah, you just need the Vaseline to lose its stick. Okay, well, you know, maybe there'll be a question on that in your exam. So what? Yeah, exactly. Right, that's interesting. So you need the glue to get weaker when it gets hot. You couldn't use like super glue. And they might ask you about what needs to stay the same in this experiment, and you would say things like the length of the rod needs to stay the same. But yeah, actually, interesting. Okay, well, thank you for making this lesson better. When I teach this again in 2 years' time, live in YouTube, I will not make that mistake. Right, that is the end of the lesson. I didn't show them this on Facebook, but I thought, see how much you're on it. One last little bit of brain exercise. Have a look at this diagram here. We've got a candle, someone's holding a metal rod, assume it's metal. The diagram shows you that heat... It's doing it again, isn't it? Why have we suddenly got a load of noise? That's weird. Yeah, you can hear it again. I think I've got rid of it. In which part of the rod are the particles vibrating the most? So you've got a rod here. In which part of the rod are the particles vibrating the most? I'm hoping that that is quite easy for you. Thanks, Ollie. In which part of the rod are the particles vibrating the most? Hopefully you're saying the particles that are the hottest are vibrating most, because when particles get hot, they move around more. So it would be the very tip of the rod here. In which part of the rod are the particles vibrating the least? In which part of the rod are the particles vibrating the least? Dexter, the coolest part. Yeah, which bit is the coolest part? You ignore the colours. Yeah, you're saying the other end next to the hand. The middle. Yeah, right. Oh, no, honestly, Actresh, the real answer is, I don't know. But we need more information, don't we? We do need more information. It would depend on whether the person has just picked up the rod, wouldn't it? Because if the person has just that very second picked up the rod and stuck it in the fire, the hottest bit is the bit that's in the fire. But surely also their hand is starting to heat up the other end, and the coolest bit would be in the middle. I don't know. It's just brain exercise, innit? It's just physics. It's complicated. Just when you think you've understood it, you've stopped understanding it. Anyway, on that note, that is the end of this IGCSE physics lesson about conduction. I hope that you enjoyed it. Next week, we're doing convection, and you need to bring at least 2 identical empty spice jars. It would be good if you brought 4 identical empty spice. What you actually need is like 2 pairs. So 2 identical spice jars, and then another 2 identical spice jars. They don't necessarily need to be the same. That would be perfect. And some hot water and cold water and some food colouring. This is another one of my favourite activities. But if you've only got 2 empty spice jars, that's okay as well, all right? So yeah, that's for the convection lesson that we're doing next week, which is already listed on my Facebook page, I know, and my YouTube channel. I amaze myself. Right, I'm going to go over to my Facebook page and see if anyone there has left me any comments and said hello. Just before I go, you'll have noticed that this lesson is free. So I had to pay to get a science degree, but now I'm just using it, spilling it into the internet for free. I did teacher training as well. It's hard work, is what I'm saying. It's not often that physics teachers just teach for free into the internet and I'm doing it, and I think you should pay me for it, is what I'm saying. That's how this job works. Everything that I do is free. The printouts are free, the lessons are free, everything's free. And I just say, if you can pay me, if you are in a position to pay me, please can you? And enough of you are, so it's my job. It's amazing. It's the most ridiculous job ever. I don't know how we're doing it, but we are. Everyone is very grateful. Me the most grateful, because look at me, look at this job, it's amazing. So there's this website called Coffee. If you go to my About section on YouTube, and you are on YouTube at the moment, if you go to my About section, there's this link to this website called Coffee. You send me £5 a month. £5 a month from all you lot is enough that it's a wage for me, but hopefully £5 a month from you isn't very much to have a qualified physics teacher teaching you physics. And you might come to all my other lessons as well. You're very welcome to come. So if you come, I will send you some nice things to say thank you. I will send you some rainbow glasses. They're actually, because you're an IGCSE physicist, they're actually diffraction glasses, which we've learned about in waves. They're awesome. They make you see rainbows. They're so cool. And I'll send you a description of how they work. And I'll send you Theory of Science magazine. This is the only thing. Bye. No, thanks for coming, mate. This is the only thing that my supporters get, that people who don't support me don't get, because obviously I have to pay to like print it and then post it to you. So if you support me with £5 a month at the moment, you are getting sent this mould issue. This is a past issue that I wrote. It comes with a home compostable plastic bag. You make the tray at the back, you put some different foods in it, you grow some mould, and then hopefully you identify them with the mould identifying article. And there's a beautiful comic about how penicillin was discovered, and some information about mould as a tutor in adventure, which I didn't know any of it until I started researching it. And if you support me with £6 a month, which most people do, then another good physics one, you get the past issue about time. So that's got an activity which I think I made it up to help you think about how Einstein's theory of relativity works, and a beautiful comic about a woman who used to sell time, and it's got a sundial in it. You can make that, some information about time zones in there. Yeah. And I mean, you can support with £9 a month if you like, and I'll send you another past issue of the magazine. The main thing is the money pays my wages and means that I can actually do this job. If people weren't paying me for this job, I'd have to work in a school, which would be fine. It'd be fine. I did not like working in a school, but I do like this better. I do. Right, I'm going over to my Facebook page. Thank you for putting up with my ad. It's so cringy, but obviously I have to say it, because if I don't say it, comments, here we go. If I don't say it, I don't make money. If I don't make money, then like I say, I mean, as I always say, and I'm not joking, my CV is an absolute train wreck now. I'm not even sure that I would get a teaching job anymore. Look, it's Joe. Joe asks if it would even need to be a pin at all. Thank you, Joe. Step ahead of me. In the Bunsen burner experiment, because it's the Vaseline that needs to help. Yeah, exactly. The main thing, isn't it? And we didn't talk about this as being something that needed to stay the same. The main thing would be that they would have to be the same weight. Oh, someone's sending me a message about the convection class spice girls. Glass or plastic? Glass is better. Very good question. Yeah, it has to be glass, actually. Yeah, it just has to be 3 identical things, doesn't it? 3 things that are the same weight, because if one was heavier, that obviously wouldn't be fair, because it would fall off first. But yeah, you're absolutely right. It doesn't need to be a drawing pin. Why are they? I guess they're light and small. I'm trying to think what else it could be. I can't think of anything. Guitar plectrums? Physicists probably more light as well. Drawing pins, aren't they? Hello, Edmund. Double glazed windows have argon in between the panes of glass, not air. Nice one. It's so hot that here that he's eaten one of his ice cubes to cool down. Not the buttery one. That's still in his hand. Edit. Now he's eating the other one too. I've never eaten a buttery ice cube. I guess that's just eating butter, isn't it? Really? But some of them, yes, exactly. Oh, hello, Summer. Is it conduction when your feet burn on a hot floor outside? Oh, that's what I should have done. That would have been a really good example. Yeah, I should have said that. Yeah, absolutely it is. Absolutely. Conduction when you step outside and you've got like maybe concrete outside and the sun's been heating up for a long time. Yes, that is conduction. Yeah, it's like the opposite, isn't it, of the ice cube activity. So heat is flowing from the hot whatever it is tiles of the ground into your foot. Yes. Hello, Freya and Hannah. Hello, that's my little, hello, long-term Science Alliance members. Good to see you. All right, Kai, we can't seem to comment on YouTube. Are you not subscribed? Are you not like logged in or something? it's a bit complicated on YouTube, isn't it? That's why I'm still doing the Facebook thing. Hello, Willow and Darcy. Oh, Neve, my birthday was last Thursday and we went to see Wicked in London. No, you didn't. Oh, so cool. Man, I'm just jealous of all of that. Jealous of the London and the singing. Happy birthday from me. Oh, Jacob, you were here. Hello, Jacob. Oh, it's Orla. Hello, Orla. I'll do a quick refresh just in case anyone's lumbered over to my Facebook page to make a comment. But hopefully you've all been able to comment on YouTube. Yeah, sorry, I'm really aware that... Oh, bye, Amber. Bye, Sweeney's. Bye. Yeah, I can look at your comments now. There's Nora again. There's Amber again. All right, Casper. Yeah, I did sort of start these lessons by saying Facebook ones have comments and YouTube ones don't have comments. And I know some people really like the fact that there aren't any comments. So I don't want... And these are recorded forever. So I don't... It's a bit sort of distracting if you're watching on catch-up. And suddenly I start going like, oh, Casper, how are you doing? It's good to see you the other day. So I'm seeing the comments go by, but I'm trying not to comment too much on them. Right, yeah, that's just Joe's comment again. Brilliant, okay. I am going to go. Bye, Matthew. Thank you for your comment popping up there. All right, yeah, so we'll see you next week. Bring you glass spice jars, but it's advertised on YouTube already if you want to have a look at that. Coffee link is in the about section. Thank you so much to the people who have been sending me money. Really appreciated. Cannot overstate how appreciated it is. It's unbelievable that it works, but it is working. It's so cool. Right, yeah, I'll see you all next week. Bye.